For the previous few sections, we've spent a lot of time really understanding how to compute derivatives of multivariable functions. And most recently, in section 13.6, we ended with understanding the gradient. In this section, we're going to expand along our notion of working with the gradient, and we're going to see how it directly relates to finding equations of tangent planes, as well as working with normal vectors. But before we do that, we need to remind ourselves of some topics that we learned about in chapter 11, in particular parametric equations of lines and equations of planes. And so if you'll recall, if we have a point given by x naught, y naught, z naught, as well as a vector, ABC, then the equation of the line through that point and parallel to that vector, we see that the coordinates of the point are here as constants, and then the components of the vector v occur as coefficients of our parameter t. All right, so make sure you're familiar with these parametric equations of a line. Similarly, we talked about equations of a plane, and so if we have a point and a normal vector, we learned this equation as n dotted with r minus r naught equals 0. And so if you carry out the dot product, we arrive at this equation. So keeping those two concepts in mind, we would like to talk about tangent planes and normal lines. So we have a definition here. Assume that f of x, y, z has continuous first order partial derivatives and that the point P naught is the point on the level surface f of x, y, z equals c. Now before I go on, I want to draw to your attention this equation. It's very important that all of your variables are on one side and your constant is on another. So all terms with x, y, and z are on one side. All right, if that's the case, then calling that left-hand side capital F, if the gradient is non-zero, then taking n, the normal vector, to be the gradient evaluated at your point P naught is a normal vector to your surface at P naught. And furthermore, the tangent plane then is just given by that gradient evaluated at our point dotted with r minus r naught, as it always has been. And so we obtain this equation for the tangent plane. Similarly, if we want a line normal to the surface at a point, well, then we just need to use, again, the gradient for our normal vector n. And we can set up our parametric equations of our normal line as such. All right, so these are the only two new pieces of information right here, these two definitions. And for the rest of the notes, we'll just be working out some example problems to illustrate these two definitions. So first, problem 12, find an equation of the tangent plane and parametric equations for the normal line to the surface given by z equals square root of x plus square root of y at our given point. So I'm going to begin by collecting all the x, y, and z terms to one side. It does not matter whether you move the x and y to the left or whether you push z to the right. I'm going to push z to the right, so I'm going to write this as x to the 1/2 plus y to the 1/2 minus z equals 0. And then I will use this expression to set up my gradient and my equations. So if I denote the left-hand side by f, then my gradient of f at any general point is 1/2 x to the negative 1/2, 1/2 y to the negative 1/2, and negative 1. So in particular, my normal vector n, which is going to be the gradient at my point 4, 9, 5, is given by 1 over 2 square root of 4, 1 over 2 square root of 9, and negative 1. So that is 1/4, 1/6, and negative 1. Once I've computed this normal vector, I am now ready to set up both the equation of the tangent plane as well as the parametric equations for the normal line. So let's start with the tangent plane. I want to take my normal vector 1/4, 1/6, -1, and I want to dot it with x minus 4, y minus 9, z minus 5, and I want this to equal 0 because I want my normal to be perpendicular to all points on my plane. And so you could leave your answer as 1/4 x minus 4 plus 1/6 y minus 9 minus z minus 5 equals 0 if you want. So I'll box this in. However, the back of the book is going to expand this and put it into standard form and stick all of the constants over on the right-hand side. So if you want to do it that way, we have 1/4 x plus 1/6 y minus z equals, the x term moved over is a 1, the y term is 9/6 or 3/2, and the z term is a positive 5, so moving over is -5. So 5/2 minus 5 is a -5/2. So this is another way to write your equation of your tangent plane. Now let's turn our attention over to the normal line. And so for this one, we have x equals the x coordinate of our point plus the x coordinate of our vector times t, and so on and so forth for x and y. So these three equations form your parametric equations for your normal line. All right, let's take a look at our next example. Find all points on the ellipsoid 2x squared plus 3y squared plus 4z squared equals 9, at which the plane tangent to the ellipsoid is parallel to the plane given by x minus 2y plus 3z equals 5. All right, we want to find a tangent plane parallel to this given plane. So what do we know about two parallel planes? So for two planes to be parallel, their normals must also be parallel. All right, so let's kind of zero in on the normals that we care about. So one is the normals for the tangent plane. So for those normals of tangent plane, we're just going to compute the gradient. All right, all of these terms are already collected on one side. So the gradient here is going to be 4x, 6y, and 8z. And I'll just denote this as n sub t for normal of the tangent plane. So what about a normal for the plane that we're given? Normal of the given plane. So that is 1, -2, 3. So I'm going to denote that by n sub p for normal of the plane that we were given. All right, we need these normals to be parallel. What does it mean for two vectors to be parallel? It means that they are scalar multiples of one another. So we need the normal of our tangent plane to be some multiple c times the normal of our given plane, so long as c is non-zero. So let's set up those equations. I want 4x to equal 1c. I want 6y to equal -2c, and I want 8z to equal 3c. All right. So what I have ensured is that the two normals that I care about are scalar multiples of one another. Now, right now I have 3 equations and 4 unknowns, so this is not a solution that I can solve. So I need to utilize one more equation. And remember, I'm finding a plane that is tangent to the ellipsoid. So what that tells me is these coordinates, x, y, z, need to lie on the ellipsoid. So what I'd like to do is solve for x, y, and z. X is 1/4 c, y is -1/3 c, and z is 3/8 c. And I need the point x, y, z to lie on the ellipsoid. So I'm going to plug these equations into the ellipsoid equation, and that will reduce this from a system of 3 equations to a system of 1 equation, 1 unknown. So remember, our equation for an ellipsoid was 2x squared plus 3y squared plus 4z squared equals 9. And so using the expressions that I have for x, y, and z, I have 2 times 1/16 c squared plus 3 times 1/9 c squared plus 4 times 9/64 c squared equals 9. So let's go ahead and do some simplification here. This is 1/8 c squared plus 1/3 c squared. 4 goes into 64 16 times, so 9/16 c squared equals 9. All right, now if you're anything like me, you don't really like dealing with fractions. So what I'm going to do is I'm going to multiply by the least common multiple of 8, 3, and 16, which is going to be the product of 3 and 16. So that's 48. And I'm just going to multiply that straight across. So that's going to reduce it to a 6c squared plus a 16c squared. 16 goes into 48 3 times, so 3 times 9 is 27c squared. And then over here, I'm just going to leave it as 9 times 48. And I'm not even going to bother to multiply that out for 2 reasons. One is because I'm lazy, and if I don't have to do something, then I'm not going to do it. But more importantly, reason number 2 is that I see that all of my c's are squared. So I'm going to want to end up square rooting this number in the end. And I might as well leave it factored so that I can find the perfect squares easier. So adding up all of the c squared terms here, I get 49c squared equals 9 times 48. In other words, c squared equals 9 times 48 divided by 49. So c is plus or minus the square root of 9 times 48 over 49. All right, so let's find those perfect squares. Remember, 48 is 16 times 3. So the 16 and the 9 can pull out to a 3 times 4 or 12. So I have plus or minus 12 root 3. And of course, the square root of 49 is 7. So we have this really awful number for C, but it's a number nonetheless. And what was our goal? Let's zoom out here and look back up here. We want to find all points on the ellipsoid at which these planes are parallel. So we already have a general setup for the points right up here that I just highlighted. So to find the final points, we need only plug this C value into our equations for X, Y, and Z. All right, so to find points, we just need to plug C into the X, Y, and Z equations. All right, so remember, X was 1/4 C, Y was -1/3 C, and Z was 3/8 C. So we're going to have 2 points due to the plus or minus. 1/4 C can simplify to plus or minus 3 root 3 over 7. Now, notice here that this Y term is negative, and so it negates the plus or minus to a minus plus. And I'm going to write that in red to really call your attention to it. A lot of times students are like, well, who cares? A plus minus is the same as a minus plus. Yes, to an extent it is, but I'm writing out two sets of points. So if the x point is positive, then the y point is going to be negative and vice versa. So by switching that order, it indicates that it's going to differ from the sign of x. So I want 1/3 of c, which is going to give me 4√3/7. And then finally, z is going to be plus minus. The 3 can't cancel, but the 8 on bottom, the 12/8 can reduce to 3/2. So this is going to leave me with a 9√3/14. All right. And these 2 points are the points on the ellipsoid whose tangent plane is parallel to the given plane. All right, we have one last example here to end these notes. We want to show that the equation of the plane that is tangent to the given paraboloid there at a particular point x0, y0, z0 can be written in this form. All right, so they're giving you the answer. There is no answer in the back of the book for these types of problems. They're giving you the answer and they just want you to prove it by running through the computation. All right, so as always, we want to make sure that all of our x, y, and z terms are on one side. So I'm going to kick the z over with the x and y terms. So I'm going to write my f of x, y, z as x squared over a squared plus y squared over b squared minus z. Now to come up with an equation of the tangent plane, I need to first find the normal, which is going to be the gradient. So that gradient is 2x over a squared, 2y over b squared, and -1. All right, so here's my gradient. And of course, if I wanted to evaluate the gradient at the point x0, y0, z0, well, then I certainly could do that. And I would write it as 2x0 over a squared, 2y0 over b squared, and -1. All right, so pulling it all together, I want to find the equation of the tangent plane at this x0, y0, z0 point. So what I'm going to do is I'm going to take my gradient, 2x0 over a squared, 2y0 over b squared, and -1. And I want to dot it with r minus r0, which is x minus x0, y minus y0, z minus z0, and this equals 0. All right, so let's carry out the dot product. That is 2x0 over a squared times x minus x0 plus 2y0 over b squared, y minus y0. And then I just have minus z minus z0 equals 0. Now let's look at what we're trying to get to, right? Our goal is this equation right here. So let's scoot these z terms over to the other side. And then I'm going to go ahead and just distribute these two pieces here in front. So I'm going to write this as 2x0 x over a squared minus 2x0 squared over a squared. And then similar for the y's. And then when I move those z terms over, I have a z minus z0 on the other side. So when I'm looking up top here, I see that I want to include these two mixed terms, which I see here and here. So those terms are fine. Let me kind of group them together out front. 2x0 x over a squared plus 2y0 y over b squared. I want those to remain. So now let's take a look at these other pieces. I'm going to factor a -2 out, and that's going to leave me with x0 squared over a squared plus y0 squared over b squared. And then of course I still have my right-hand side of z minus z0. So I would like to completely get rid of this term. And furthermore, this is the wrong sign, right? I'm hoping for a plus here. So if I look all the way back up at the original function, the original equation of the paraboloid. Notice that x squared over a squared plus y squared over b squared is z. Well, that's almost exactly what I have here, except for with the subscript zeros. So what I can do is I can use that equation and plug it in here, and I'll rewrite my first two terms. And this is going to all collapse to a minus 2z, z naught that is, because I have x naught and y naught. And this equals z minus z naught. And hot dog, we can add it over to the other side. And we conclude that 2x naught x over a squared plus 2y naught y over b squared equals z plus z naught, as we were supposed to show. All right, so this concludes our section over tangent lines and normal vectors. Looking forward to the next section, we'll be talking about maxima and minima of functions of two variables, so stay tuned.